Hello and welcome to the latest podcast from Anritsu. My name is Paul Holes. I'm the RF and microwave applications engineer working primarily in the UK but also across Europe. This podcast is about pulse VNA measurements. So the topics we are going to discuss today are common pulse applications and use cases, including pulsed RF and pulsed IV with associated RF. We're going to look at the pulses in time and frequency domain and what are the historical and traditional trade-offs of this kind of measurement. What are the common test challenges that engineers face? And then moving on to our Anritsu approach of this measurement, our differentiation and our user interface. And finally, discussion regarding our coupled IF receiver windows and a summary. Pulse test parameter and related measurements are critical for many common applications. The tests of a system are subsystems designed to operate in pulse conditions. A pulse system and subsystem measurements that may be needed examine phase and amplitude distortions at pulse onset or droop later in a pulse, as well as in cases where the subsystem was designed to operate pulse. Or the measurement of devices and components that are designed to operate in pulse conditions. Device characterization, where pulsed operation is required for thermal reasons, for example, unmounted power devices. Or device characterization, where pulsed operation is required to explore certain device characteristics. Trapping and thermal parameter characterization are two common tasks that benefit from pulse measurement. Pulse test parameters are typically part of a suite of tests on a device, component or system, which may include S parameters, the 1 dB compression point, noise figure, higher order distortion products, harmonics, IMD, or IP3. Radio detection and ranging. When we speak of radar applications, must keep in mind all of the different varieties of radar systems. They operate at many different frequencies. They can be used for military or civilian applications. For civilian applications, two of the more popular are weather radar and automotive driver assistance systems. So if we look a little more at the radar test application, there are many factors which can affect radar system performance, and engineers use equipment to test a number of them. Pulse shape determines the range accuracy and a minimum maximum range. Ideally, they require perfect rising and falling edges and a minimal overshoot. The pulse width determines range resolution. A longer pulse provides more power range but less resolution. A shorter pulse gives you less range but better resolution. The PRF determines maximum unambiguous range. The maximum range from which a transmitted radar, LiDAR or SODAR pulse can be reflected and received before the next pulse is transmitted. And the fundamental frequency determines the antenna size, the beam directivity and the target size. And other factors as shown in the table affect the radar characteristics. So what are the trends? The trends we're seeing in this area is there's a move to narrower pulses for better resolution. So 1 microsecond pulse width gives you 150 meters resolution, while 50 nanoseconds gives you 7.5 meters. There is a need for systems to cover a wider range of PRFs to adapt to different uses. So lower PRFs gives you a longer range, while higher PRFs gives you faster response time. Also, higher frequencies allow for a smaller antenna size and give more available bandwidth and allow identification of smaller targets. So when selecting a VNA with pulse capability, the key measurement parameters often include minimum pulse width resolution, recording length, range of PRFs and frequency range. Applications that utilise pulsed IV and sometimes RF as well include the testing of TWTAs or travelling wave tube amplifiers. TWTAs can consume a lot of power, so users prefer to use pulses to turn it on only when needed. Pulsed IV is also used for wafer level testing to avoid thermal effects such as memory and trapping. Memory effect causes a hysteresis. After a device heats, it may not return to its former state. For example, it may result in drawing more power over time. Trapping is a parasitic effect where holes or electrons can get trapped, reducing conduction, which can reduce the output power a device can provide. Pulse characteristics and definitions. Used when making pulse measurements, this gives us some common terminology for the remainder of the presentation. Here we have the peak power. Note from the top of the pulse down to 10% of the average on power. We have the rise time and the fall time. These are normally measured between 10 and 90% of the average on power. Droop, or sometimes known as the slope, between the average of the peak to the falling edge and the fall time. Down here we have the pulse repetition interval, so we have two pulses here. The PRI, pulse repetition interval, is the time between the leading edge of the two pulses. The pulse width is taken at 50% the average of the peak on power, and the average off pulse power is the middle 80%. So let's look at some use cases. Use case 1 is a radar system component test using a 2-modulator test set. The user is testing a component in which the normal use is with a unidirectional pulse for a typical component characterization. In scenarios 1A and 2, a radar system component test is using a 2-modulator test set. The user may either be testing a component in which the normal use is with a unidirectional pulse, but the user wants to include the response to a reverse direction pulse for a complete component characterization, or in 2, or a TR module in which bidirectional RF pulsing is required. Use case 3. On wafer power amplifier device test with a CWRF and a pulsed bias. The user will utilise internal pulse generators to control the bias to the on-wafer device to compensate for the lack of availability of a heatsink and to minimise thermal effects. Use case 4. On-wafer power amplifier device test with a pulsed RF and a pulsed bias using a 2 or 4 modulator test set. The amplifier intended end use is a pulsed application commonly for use in a radar system component, and so the user will stimulate the device with a pulsed RF signal, as well as utilise the internal pulse generators to control the bias to the on-wafer device to compensate for the lack of a heatsink and to minimise the thermal effects, and therefore the timing between these pulses is important to ensure the RF is applied to the device while it is turned on. Normal use of the device is with a unidirectional pulse, but the user wants to include the response to a reverse direction pulse for a complete component characterization. In scenario 5, the bidirectional antenna test with pulse signals. The user may be concerned with leakage from a large pulse transmit signal saturating the receiver, and will use a 4-modulator test set to both pulse modulate the RF as well as gate via pulsing the received signal. And on the table down here you can see the use cases and the number of modulation boxes required to do those measurements. So in scenario 5 it's used in less than 5% of cases. So pulse modulation test sets, receiver modulators. As discussed in the previous slide, used in specialised use cases, in antenna test applications where leakage signal may saturate the VNA. The PMTS pulse modulation test set has insertion lock, so you do not connect the paths unless you need them. So why would you want to gate the receiver? Well, here we have a transmitter and a receiver RX, and we are trying to measure the echo of a target. Typically this signal is fairly high power, and these two antennas are usually located fairly close together, and you get some leakage from the transmitter into the receiver. And that can result in all kinds of negative effects. So to lock out the leakage signal, you would need to use some kind of gating by opening the switch so you only see the signal returning from the target. Another application would be antenna range again, where something inside the range, like a stand the target sits on, or something inside the range which provides an unwanted reflection. So before discussing the various pulse measurement methodologies, it's worthwhile to do a quick review of pulses in the time and frequency domains. When a signal is switched on and off in the time domain, i.e. pulse, the signal spectrum in the frequency domain has a sin x over x response. This means that the width of the lobes is inversely related to the pulse width. Consequently, as the pulses get shorter in duration, the spectral energy is spread across a wider bandwidth. The spacing between the various spectral components is equal to the PRF, pulse repetition frequency. So let's look at some traditional trade-offs. So historically there have been two common methods for making pulse measurements, wideband and narrowband. The wideband pulse measurement method may be used when the majority of the RF pulse is within the bandwidth of the receiver, which has been in a range of 5 to 10 MHz. As pulses become narrower, their spectral content spreads. So consequently this technique limits the pulse widths to a few hundred nanoseconds or more. To address narrow pulses, the narrowband method has been employed. This method capitalizes on the fact that the central spectral line carries the magnitude and phase information of the underlying RF signal, FC. After filtering out everything but this frequency, only a CW signal remains and standard VNA processing may be applied. The advantage of this technique is that narrow pulse widths can be measured. The lower limit is primarily limited by the overall system IF bandwidth and associated aliasing avoidance, while the profiling measurement resolution is limited by the receiver gating capability. The biggest limitation of the narrowband method is that dynamic range becomes a function of the duty cycle. Since only the central spectral line is kept, a significant amount of energy in the remaining spectrum is discarded, particularly as the duty cycle shrinks. And as the duty cycle becomes smaller, there is less power in the RF carrier signal, which affects this method's available dynamic range, and the receiver becomes desensitized. The result is a dynamic range penalty of 20 log 10 duty cycle. For a duty cycle of 1%, the average dynamic range is reduced by 40 dBs. So what are the common test challenges facing engineers today? There's too many test method trade-offs. Existing pulse test methodologies require trade-offs to be made based on the required duty cycle, pulse width, dynamic range and more, as previously discussed. There's a need for better analysis tools, whether you're tracking high-speed targets or detecting slow, low and small objects. Better analysis tools are needed. Next generation radar systems require greater precision to measure narrower pulse widths and or to examine intrapulse behaviour with finer resolution, including rising and falling edge effects. There's a need to monitor pulse behaviour over longer times. In some applications, observing behaviour over longer periods of times without sacrificing resolution may be important, whether it's looking for thermal and trapping effects in devices or measuring device under test with lower pulse repetition frequencies. Eliminating measurement setup errors and ensuring proper measurement setup and timing alignment can be challenging, especially when measurement solutions require the user to toggle between setup and measurement screens. And then we have timing and synchronization issues in measurement or calibration. Calibration under pulse conditions adds an extra degree of challenge. Timing and synchronization issues create uncertainty and can include unwanted behaviors. The Anritsu VectorStar MS4640B series of VNAs, equipped with options 35 and options 42 addresses these challenges with a number of industry firsts to deliver confidence to your measurements. With these trade-offs discussed in previous slides, with these new options with VectorStar, these can be eliminated. With our high-speed digitizer measurement method in VectorStar, represents a major technology advancement over prior pulse measurement methods. While similar to the historic wideband method, this method is based on direct acquisition, but at a much higher data rate than was previously available. VectorStar offers a digital IF acquisition system with a 200 MHz bandwidth, and as a result, resolutions are enhanced and time referencing becomes much more accurate. The exact acquisition method differs in that the acquisition itself is not controlled by the pulse system, except in the case of pulse-to-pulse measurements. Portions of the data can be recorded to be analysed and correlated with the pulse pattern being used, and this enables the ability to have independent receivers, which we'll talk about later. Since no energy is being discarded in the high-speed digitizer pulse measurement method, there is no duty cycle dependence, and full dynamic range is now available. Prior to the release of the pulse capability on VectorStar, competitive solutions only offered up to about 15 nanoseconds minimum measurement resolution, and with that resolution the customer could be missing some valuable information. In this example, the overshoot and undershoot were missed. In sensitive receivers, this overshoot could be pushing the receiver into compression and the customer wouldn't know it. However, they may see effects like spectral splatter and may not be able to determine its cause. With PulseView, customers get the true view of how their device under test is behaving. PulseView offers the industry's longest pulse measurement record length. Other solutions can have more than an order of magnitude shorter record lengths. Moreover, the PulseView records can be saved with full 2.5 nanoseconds resolution, up to 500 milliseconds. So the PulseView software allows us to control the stimulus and the measurements in a very user-friendly way. 3 types of stimulus provided by the PulseView software. 1. Modulating the RF of a device under test, and that requires a test set. 2. Modulating the voltage current to the device under test and doesn't require a test set. And 3 is a hybrid of both, so we have a lot of flexibility in the stimulus that we can provide. 3 types of measurements. Pulse profile. This is where we are looking at the CW envelope, the pulse envelope of a CW signal, and we can resolve this in very high resolution. Where we may wish to sweep in time and measure how the amplifier or modulator is going to impact the RF signal passing through it, i.e. rise time. Point in pulse. This is useful because we can pick a point anywhere in the pulse train, typically away from the edge effects. They can sweep frequency or power, and you can look at a pulsed S parameter, gain compression. It's a steady state type of measurement. And finally 3, pulse to pulse. This looks at behaviour from one pulse to another, i.e. S21 phase from pulse 1 to pulse 3. Here we show an example of the pulse profile display on our VectorStar Vector Network Analyzer. You can clearly see the parameters required on the right hand side shown clearly in the display. Pulse modulator test sets. We have 4 pulse modulator test sets, 2 at 40 gigs and 2 at 70 gigs. We have options for 2 source modulators, 1 in each direction on the stimulus, and options for 2 source modulators and 2 receiver modulators where you can gate the receive signal. The PulseView graphical user interface window enables customers to visually confirm their test setup and measurement configuration. This provides greater confidence in the results they get. The 4 internal pulse generators can be configured with one of 5 signal types: singlet, doublet, triplet, quadruplet and 5 burst. This configuration enables users to generate a series of equally spaced pulses with the test system pulse repetition interval. The screenshot shows a 50% duty cycle, but the users can define the duty cycle generated with the burst pulse period and width parameters. To further help the user with ensuring they have the proper test set up, the pulse generators can be labelled to keep track of which generator is being used for which function. As previously mentioned, there are three types of pulse measurement available: pulse profile, point-in-pulse, and pulse-to-pulse. Once the measurement type is selected, VectorStar's 4 receivers can either be configured all at once with the same parameters, or they can be configured independently. A benefit of independent receivers will be shown shortly. For all duty cycle applications, much of the activity is concentrated in a small section of the pulse repetition interval and may be hard to see. With the zoom marker feature, users can zoom in to ensure they have the timing they require. Just drag the two vertical lines to select an area and press zoom in. Additionally, the vertical lines display the time within the PRA at which they are located, enabling them to be used as time markers. So why is it necessary to have a lot of flexibility in the setup? Well, sometimes we get unexpected results. So above is a pulsed S parameter measurement that we are trying to make over this time frame. Flat pass of the left hand side trace. There may be some delays or timing issues due to the external cables, etc. And this is where PulseView helps us out a lot. On the trace on the right, we can see the stimulus window and the measurement window. In here you can see that due to a delay in length of cable or device under test, they don't occur at the same time. And as the S parameter is basically a ratio of the two, you need these two to happen at the same time, and they aren't, so the data on the left hand side trace is pretty meaningless. So now we can set up the independent receiver windows. This allows you to adjust in time each receiver independently. So we look at the display and see the difference between the two and add a delay into the pop-up window. This allows us to align the two traces and allows us to get the measurement correct. Unlike other VNA pulse measurement solutions, VectorStar enables users to measurement adjustments and see the results instantly in the PulseView setup menu. With VectorStar, there is no need to toggle back and forth between configuration windows, which is time consuming and prone to errors. One of the things that we retain throughout our pulse capability is to go up to 110 GHz and also up through the THz region. Test sets only work up to 70 gigs, but the measurement software and stimulus provides the capacity to go there. So what does Anritsu's VectorStar give us with its new pulse options? It gives us an innovative high-speed digitizer architecture with the highest resolution measurements, the longest recording lengths and independent measurement receiver windows, an intuitive graphical configuration tool, and allows us to see instant results on measurement parameter changes. This video podcast. Thank you for listening.